And here we are again in our next chemistry lesson. And as before, starting with worth pausing and just checking through. Do you know them all now? Are they all stuck in your head? Will you remember them all? The fact that if you lose an electron, you become positive. Positives and negatives have electrostatic bonds holding the ions in place. And then the covalent bonding we've been doing recently. And then the new rules that are added on here. Have you got those written down? So, first things first, make sure you're comfortable with the rules, and then we'll move on with today's lesson. And we did a lesson about carbon being special, and now another lesson about carbon is even more special than you thought. I know what you're thinking now. You're thinking, how special can it be? Well, it's that special. This is supercarbon. Carbon, from what we know so far, from the lessons we've done, it's in group 4. Carbon makes 4 bonds. We've done that. Carbon, so far, can actually, pure carbon with 4 bonds forms diamond. And you should be able to straight away go 4 bonds, extremely hard to break them apart, makes it the hardest natural substance that we've ever found, formed under high pressure and high temperature underneath at the base of the Earth's crust, so it's rare. 4 strong covalent bonds, no weakness. And more common form of carbon is graphite. And that's where it settles for 3 bonds. And it has spare electrons. So far, you're probably thinking, yeah, fair enough. I'm really quite impressed with carbon. Wow, carbon's really cool. I wish I was that cool. Oh wow, look, I can draw little lines on him. I can even improve his boots. We can have a lightning strike. There we go. Oh. Evil eyes. Shh. There we go. That's supercarbon, man. I know what most of you are thinking. Looks a bit like me. Yes, he does. What's even more special about carbon then? Because actually that's just what we learnt last lesson. What's even more special is diamond and graphite aren't the only forms of carbon. We've also dealt so far with how carbon can make simple covalent structures. So the fact that carbon dioxide, a gas, methane, a gas, carbon monoxide, a gas, and so on and so on. Carbon can also make chains, and you'll do more about a whole area of organic chemistry in year 11, but carbon can make great big long chains, and actually most of you is made out of carbon. Proteins, fats, carbohydrates, all based on carbon. But that's not what makes it even more special. So actually, Carbon Man is one thing, but a different way of remembering it is the Fantastic Four, because carbon has 4 different forms. 4 forms. We have dealt with number 1, diamond. We've dealt with number 2, graphite. When you have different solid forms of the same element, carbon, they are called allotropes. Carbon has 4 allotropes, is a better word than 4 different forms. And like I say, we've already dealt with 2 of them. So, some questions just to refresh memories. Please pause, have a go, and then we'll go through the answers. Right, I'm trusting you've paused and you haven't just carried straight on to this. How much does a proton, a neutron, and electron weigh? Well, we say that a proton weighs 1 atomic unit, and a neutron weighs 1, and an electron weighs 0. Because it's so small, we actually call its mass 0. How are diamond and graphite different? You can have several for this. 4 bonds here, 3 bonds here. Very hard, like most people in Portsmouth. And graphite, 3 in layers. Slippy layers that slide over each other. and conducts electricity. So, and what do we call atoms of the same element with different numbers of neutrons? Now, I've deliberately put this one in because allotropes are different forms, like diamond and graphite are allotropes because they're all made of carbon. This one is the same element but just different numbers of neutrons. And when we first did this, we said chlorine 37 and chlorine 35. They are different numbers of neutron even though they're both chlorine, and those are called isotopes. Now, hopefully you've got most of that correct, or bits of it, and you've made corrections as you go along. So, we've dealt with this. Carbon makes simple covalent molecules. Carbon with its 4 bonds is the giant covalent structure. Diamond, that's number 1. Number 2, carbon can be graphite layers, like in your pencils. Conducts electricity, so it's got loads of uses. And now we come to the new bits. After you've done these questions, obviously. So a couple of questions there to check your understanding of giant covalent. And this one starts with silicon dioxide has a giant covalent. What would its properties be? And hopefully you're thinking, its properties, because it's giant covalent, it would be a solid. And it would have probably a high melting point from all those strong bonds, the giant molecule. And it's probably quite hard. And then it says here, silicon dioxide is used to make moulds. Now, moulds for pouring liquid metal into. So it might be the mould to make a spanner, and they pour the liquid metal in and it cools down to the shape of a spanner. Why can silicon dioxide be used for that? What is it that makes it suitable? And again, it's the high melting point. Right, slightly harder question on the other side. One to put in your notes. Why can you not use melting point to tell the difference between a giant ionic lattice with the ionic bonding or a giant covalent structure? What is it about their melting points that wouldn't allow you to tell them apart? And now, a mysterious the future slide. Wow, what could that mean? And what it means is, in more recent years, I wasn't taught about this at school, and I'm almost 21. A recent discovery has been this single layer sheet of carbon, like graphite, but it's called graphene. It's a single layer. Now, when they first discovered how to make graphite into a single great big layer, what they discovered about it was it is very, very, very strong. The free electrons in graphite that allow it to conduct electricity make really strong electrostatic bonds that make it incredibly strong. The strongest material ever for its size. Remember, 1 atom thick. So a single layer, very, very strong. If it was a similar thickness of Kevlar, bulletproof vest material, this is stronger. So could this be bulletproof for the future? Could we have bulletproof clothes with carbon graphene in it? That's a question. It's amazingly good at electricity conducting. There is very little resistance. It makes it perfect for all sorts of things like touchscreens or even TV screens. I remember talking to one of my classes last year and suggesting maybe we can have extremely thin TVs, flexible phones. Maybe it's just a patch on your arm. Then we started talking about what if you made a hoodie and the whole hoodie material was extremely thin, graphene coated, and you had a TV program showing on it. So then you go to the jungle and you show a program about the jungle and you merge in with it. So camouflage, or in fact, the uses of graphene were right at the start scientifically of how it could be used. So that's why the future slide. What you need to know for now is graphene is a single layer. It's an extremely strong, really good at conducting electricity material, has loads of potential uses in touchscreens and all sorts of modern technology. So pause there and just explain the main features of the allotrope graphene, and then, what a lovely name, Buckminster fullerene. This is similar in a way to graphene, that we've got these carbons with 3 bonds, just like in graphite and graphene. And actually, these shapes are hollow spheres. Very strong. Very good at conducting electricity. Seems a bit similar to graphene at the moment. What we've talked about developing the use of these is you could package substances inside these for delivery. Could we deliver medicines to different parts of the body where they're needed? Some of the smaller fullerenes, because this is just the Buckminster one, which has 60 carbons in it, but there's other size fullerenes. Could we have fullerenes, and some of them are quite good at entering the brain? So what could we be delivering to different cells around the body to help with issues? So again, we're at a really early stage. So for me to say, oh, fullerenes are used for this, this and this, we're looking at what they can be used for, and the science on this is changing every day. Something that will probably feature quite heavily in your life. When I'm teaching this in 20 years time, when I'm 41, I don't know, it might be a whole topic to itself, all about Buckminster fullerenes. And then the last one, and I said there was 4 because this really is like graphene, and I haven't given this one a number. Just the fact that we can take these incredibly strong graphene sheets and we can have tubes of them. Now, nano, and there's a reason for this. These are tiny, extremely strong. And when I say extremely strong, they are much stronger. I'm going to put a greater than, much stronger than steel of the same size, as in 100 times stronger than steel. What does that mean in terms of when we can use these and get them really long and get loads of them easily, when we can make nanotubes quite cheaply? Are we going to be able to use them in buildings? How thin could the walls be if these are 100 times stronger than steel? Are we going to be able to use nanotubes in bikes, cars, where we have things at the moment that are quite wide supports to carry a heavy weight? Will we be able to have incredibly thin supports because they're made of carbon nanotubes? So again, real area of interest for scientists in how we can develop them and the use of these, how we can produce them much easier, and therefore how we can use them after that. So based on all of this, before you go on to these questions, make sure that you've paused enough. Make sure that you can allotropes 4 diamond, 4 graphite, 4 graphene, 4 Buckminster fullerenes, and for the nanotubes of graphene, can you give the main points? And by that I mean you'd go, graphite, 3 bonds, 3 electrons, 3 bonds, 3 electrons, conducts electricity, fairly cheap. So can I give the main points on each of the allotropes and how they're arranged? So some little diagrams and some little notes, and if you need to go back to any of the previous slides, do so. Then some questions here for you. So you're going to pause now and you can have a go at these questions. Why is diamond so hard? Why does graphite conduct electricity? Why is graphene so cool? So pause, and when you're ready and you've done the questions and answers, mark your own work. I'll go through them. Welcome back from your pause. Why is diamond so hard? 4 covalent bonds holding atoms in a giant structure. Very hard to break. That's why it's strong. Why does graphite conduct electricity? 3 covalent bonds, free electrons, can move and they flow through the graphite, and that's what electricity is. And why is graphene so cool? It's very, 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 well, it's 1 atom thin, and it's got an immense strength and electrical conductivity. Now, why is it so cool? It's really strong, it's really thin, it can conduct loads of electricity, and actually the reason it's so cool is we haven't got a clue yet what people are going to be able to invent with this. Right, thank you very much for listening, and hopefully you learned something, and we'll see you next time for a little bit of Metallica. Brilliant.